Thank you very much. And today, I try to introduce our university histories and our labs activities. So this is the model, 3D model, which we built 10 years ago, auditorium. It is about 10 minutes from the center of Tokyo. And the right hand of this auditorium, 7th floor, we have our lab. And Professor Nakamura's lab is 8th floor. So when you visit here, please come and see our activities. So in our university, the professors of the Department of Mechanical Engineering started robotics and the computational machine around middle of 1960s. Then, Professor Inoue was a student of that lab, and he did this work for his PhD thesis. At that time, computer was very small, 4 kilowatt memory, but he built these end effectors, about more than 20 tactile sensors, and it can read the servo error of each joint, 6 degrees of freedom arm. Then the environment can navigate the robot motion based on its state. So his program showed this achievement, and this is, at that time, no keyboard. So he used this hand end effector as the input device to tell his intention to execute these motions. That was 1969. And I always show this movie for the young graduate students in my lecture. So the recent robot cannot show this kind of dexterous, very fine motion. The student just calculate, close eyes and move, then it's okay. So such kind of, logically it should be, but in real world, the robot have to take more sensor-motor interaction in the loops. So that was about 50 years ago. Then I became a student in 1981. Then he was an associate professor in this lab, our lab, and we did this kind of hand-eye coordination using the single camera and the single manipulator to make a nut. Flexible object requires visual feedback. So I put a 4 mirror in front of the camera, then it takes about 10 minutes. But all the program written in the computer language, Lisp. Our robot still, we are using the Lisp to describe the higher level and the intermediate levels. So that was first work I learned in the research lab. But after get my PhD, I wanted to change the body of the robot for the whole body, like a mobile car and mobile manipulators and animal-like quadruped, ape-like, and humanoid, and distribute to different hybrid modules to collaborate with. Then at that time, the computer was too big, so I decided not to use computer on board, just wireless communication. Send the command to the body and receive the sensor information as a camera, integrating all the sensor into the single stream of the camera. Then we could make a loop from all the sensor to the body. Then students could show many behaviors like this, but the important part is the visual processing. Here you can see that image correlation can allow us tracking the target object. So in the robotics, the detection of the target and the tracking is the key for their behaviors. But we built our own special visual tracking device. Then we could design these kind of small robot behaviors. We can build many different degree of freedom's body. The student builds these robots in 2 weeks or 3 weeks. Then they can share the software in the remote brain site. Then they can learn many things. And after that, the Japanese company produced that tracking vision for the embedded robotics. Then one student wanted to show that area swing behaviors like this. This is the top view of the room. The left-hand robot has this 2 cameras. Then here's the back. There's this vision, and have the capacitors for the battery for this vision. Then it can continue this motion as a master course thesis. So at that time, 3D flow detection tracking was the key for this kind of real-time control. And then around here, we could start the different streams of the humanoid, because the small robot is good for prototyping, but we wanted to extend for the life cycle to utilize usual tools, which is designed for human, so life-size streams, and also more complex musculoskeletal, like our body with spines. So in middle of the 90s, we started this humanoid series. And after this development, H series, H6 and H7 hardware, we asked the company, Kawada Industry, then they could provide hardware part, then we put our own software on the hardware. Then Japanese government started 5-year project for the humanoid platform from 1998 to 2003. HLP2 was born. After that project, university students could start to use this platform for their study and research. Then these are the students tried to show the demonstration with this platform. They could enjoy to design what kind of task should be done, this kind of life-size humanoid. So in the undergrad course, we provide that environment, then they can learn what's the problem. And after graduation in the master course, they try to have their own goal for their master course thesis with this platform. And so one student wanted to show some cooking. And he built everything, visual recognition, and tried to use the different tools for cooking and achieve the making salad. On the kitchen, there are many metal parts, so they have to learn how to select the attention area based on some sequence knowledge or the task descriptions. So this kind of the goal setting challenge provides students many important challenging mind, and they have to learn how to solve the problems. And another student, she wanted to make a humanoid to clean up the laundry closet. So in 2 or 3 years, they could show this kind of task sequences as for their master thesis final defenses. And another student, he wanted to assist this kind of support. He had to learn how to recognize this part and how to recover when it fits during this motion, then they have to show this kind of. So the HLP2 became a very nice platform for educational use and research for the master course. Then the doctor course, they had to show that the research papers, then one PhD student, this kind of the task sequence execution. In his demonstration, his system automatically generates a transition network during the motion. Then the structure is initially the human provide, but transition real data instance created during the motion. So that transition is controlled based on the reactive force from the environment. The idea is the same of the Professor Inoue's first 50 years ago, but in this robot, it has 4 6-axis sensors in wrist and ankle. Then the robot can keep the balancing and reactive based on the reactive force change, saturation or impact or, yeah. So changing point detection is the key for his PhD thesis. And recently, another student wanted to make this robot to ride this Segway type, cheaper Segway. But you know that the riding is difficult, even in the human. So he solved the problem, learning to ride, and also learning how to navigate, control the velocity based on the recent 3D real-time vision, the visual odometry and the SLAM capability assist this kind of motion in this room. So HLP2 provided us so huge, many different research thesis, master course and doctor course. But for the industry, they did not want to keep all the body. So they asked it just vision and just arm and not legged, wheel-based. So, but the important point is in the university, every year we have the newcomers, new student, then we have to hand over from the senior student's result to the new student. So then Humanoid, which has everything. So it is easy to keep the single platform for the many different requests. So the different companies' request, we can just use the subpart of the Humanoid software to adapt to the different shape of the body. So that was 10 years ago. So such kind of the special robot can be created from Humanoid. So, but after this research, independent research, we can combine together. Then we can keep the inheritance software platform to abstract, generalize. You know that the bigger software that become terrible. So we have to teach the student. You have to keep the size smaller, but the capability is bigger and bigger. So it requires generalization and the mind of the abstraction. So that is a basic, very important teaching term in our lab. So, but you know that around here, 10 years ago, ROS community started. So the student wanted to integrate them, but the idea that I always try to teach how to use, how to see, how to look, how to watch the outer open source communities. And those small type and medium and complex musculoskeletal, each robot has more than 100 motors in body, so it have to learn how to control its own body, spine, limbs, and muscles. But we try to continue those streams in the humanoid development. One is the musculoskeletal. This is the current version. This is seventh version. We started from middle of 1990. Then the recent body needs strength, so we had to use metal or fiber enhanced material to make the body, and many sensors. All this body designed inside the computer, and students have to build everything, mechanical design and electrical design and embedded software and intermediate software and the higher level. Higher level, task level, we can share the HLP2's environment, but the lower real-time layer and the intermediate online identification embedded layer should be, they have to build. And yeah, this is the name is Kengoro. It has a five-finger hand which can hold its own body weight, about 50 kilogram, and it has special cooling mechanism. The bone has a polar structure inside, and it cools down its bone, and the motor is attached to the bone. Then vapor, latent heat is used for the cooling the body. So those problems that student design, find the problem and find the solution to achieve this kind of. And recently the company wanted to apply this robot to show some demonstration like this, so that inside the car, robot have to adapt its own body, full body to the environment, seat, and narrow gap in the space. So from this experiment, the student can find the problem and the next goal for their own thesis. And the stream of the middle, after HLP2, HLP2 is designed the intermediate power and the speed. Torque is 1/3, and speed is also 1/3. But he wanted to make the robot to have the same power, same torque and the speed with the human. And he built motor driver and a water cooling system. Then 60 kilogram weight could jump about 30 centimeter and push recovery and make a shaft company to join that DARPA Robotics Challenge. And this is the remote control, but the team showed a very good result as a trial. And with this research, we could build our own full body humanoid with liquid cooling systems and improved version of the motor driver. Then we could, the students can show, they want to show that their own idea with this robot. And also the disaster environment, the water environment, we have to learn what is problem and how to make the system to adapt to the environment. So if we use this kind of suit, then inside the suit, we need the heat control. Without heat control, it cannot continue the actions. And also, last year, the master course student showed this experiment. So he learned many theories and control method and used this robot named Jackson. So after this research, he joined the company, but after this experiment, the current student tried to show more. And we are trying to improve the very important key element. Right now, it's motor driver. The communication link should be more robust, and also that the speed should be faster. Then one PhD student showed that while it's walking, it can show that 3 minutes, okay, recovered. So, and also that we try to apply that motor driver for the prosthesis. He joined our lab to build for his own leg active. But for everyday use, the passive, the power source is a big problem. So he designed the legs should be hybrid, the passive and active. So it requires some back drivable combination from the actuator to the leg. And also I asked the Japanese company to build more distributable platform for this humanoid community. So Kawasaki Heavy Industry built this platform for the research and for the application of the disaster. And also after the small robot, we want to send the robot to the disaster site. Then one student built this stand-up drone and fly and float. And also we can apply that result for the forest maintenance, building map of the trees. And also they started to the deformable drone in the air. And also this is a recent result of the three-dimensional deformation in the air. So those multi-link, multi-rotor body could be inherited from the humanoid activity, so that from today I wanted to show this kind of series of our student activities from the small robot to the middle and the complex and the lightweight application. And this is the final slide of today's talk. Skipped. Oh, yeah, this is, yeah, from small and industrial collaboration, open source collaboration, and life size, smaller, lightweight, and the complex one. So thank you very much.